Today, we're totally demystifying a piece of tech that's honestly the unsung hero of our modern world, the network switch. We're going to trace its evolution from clunky manual switchboards all the way to the lightning-fast hardware powering the internet today. It's going to be a fun ride seeing exactly how your data safely navigates the digital world. All right, here is our roadmap for this explainer. First up, the dawn of networking, followed by hubs and their major limitations. Then, enter the network switch. We'll peek inside the CAM table, break down the core switching process, and wrap up with the types of modern switches out there. Section 1. The dawn of networking.
So, to really grasp modern switches, you kind of have to look at the historical problem we were trying to solve. Getting a message from point A to point B without it getting totally scrambled. Think back to 19th century telephone systems. They literally required a human operator managing a physical switchboard, manually plugging in cables to make an electronic path. And creating paths is exactly what switching is all about. But, as computers hit the offices in the 70s, manual circuits just weren't going to cut it. Early networks basically just daisy-chained standalone computers together in loops. But here's the kicker. If one cable broke, boom, the whole network went down. That headache eventually brought us hubs in the 80s and finally intelligent switches in the 90s.
Moving on to Section 2, hubs and their limitations.
Let's talk about that 1980s solution. Now, a hub might have looked like a sleek central box to plug your cables into, but internally, it was basically just a bundle of wires acting like a giant chaotic megaphone. If one computer sent data into a hub, the hub just blasted it out of every single other port. Because hubs operated on a single shared physical medium, the entire network became what we call one giant collision domain. Seriously, if two devices tried talking at the exact same millisecond, their electrical signals would physically crash into each other, completely corrupting the messages.
Because of that chaos, hubs forced networks to use half-duplex communication. Think of it exactly like a walkie-talkie. You push the button to speak, and while you're talking, you literally can't hear anyone else. To manage this on a hub, computers relied on an algorithm called CCNA-CD. Sounds complex, but it basically just meant listening to the wire, waiting for dead silence, and then crossing your fingers and trying to transmit. If a collision happened, both machines would wait a random amount of time and try again. It worked, sure, but as networks grew, it just absolutely tanked performance.
Which brings us to Section 3. Enter the network switch.
By the mid-90s, networks were basically choking on their own traffic. And that is when the ultimate intelligent traffic director arrived. Going from hubs to switches was a massive, game-changing leap. See, a hub is a Layer 1 device on the OSI model. It only deals with raw electricity. But a switch? That's a Layer 2 device. It actually has intelligence. The greatest trick the switch ever pulled was splitting every single port into its own completely separate collision domain. With each port isolated, collisions were virtually wiped out, which finally opened the door for full duplex communication. Computers could actually send and receive data at the exact same time at wire speed.
To pull off this magic trick, switches rely on MAC addresses. We're talking about a unique 48-bit hexadecimal identifier that is permanently burned into every single network card right at the factory. So theoretically, no two devices on the entire planet should ever have the same 48-bit MAC address.
All right, Section 4, inside the CAM table.
So how does the switch actually memorize where all these 48-bit addresses live? Well, when you first pull a brand new switch out of the box and plug it in, it is totally clueless. It has this empty space in its memory called the CAM table, or Content Addressable Memory. But it doesn't use clunky software to learn addresses. Nope. A switch uses an ASIC chip, Application-Specific Integrated Circuitry. This beautiful piece of hardware lets the switch memorize and map devices into the CAM table as fast as electricity flows. It goes from being a shouting megaphone to a private, highly targeted courier.
Let's walk through a real-time example. Imagine computer A wants to talk to computer B. Step 1, computer A sends out an ARP message, an Address Resolution Protocol broadcast, basically yelling, "Hey, who has computer B?" The switch receives this on, say, port 1. Instantly, in step 2, the switch learns computer A's MAC address and jots it down in the CAM table next to port 1. Now, it doesn't know where B is quite yet, so it floods that broadcast to everyone. In step 3, computer B hears it and replies. The switch catches that reply on port 2, and for step 4, logs B's MAC address. Boom! Mystery solved. From that exact moment on, traffic between A and B goes directly between port 1 and port 2. The rest of the network doesn't hear a peep.
Next up, Section 5,
The core switching process.
Once that CAM table is populated, the switch just continuously runs a very specific logical routine. There are 5 core functions of a switch that you absolutely have to know. First is learning. It's constantly reading incoming data to record those source MAC addresses. Second is flooding. If it gets data for a destination it doesn't know yet, it just sends it out every port to be safe. Third is forwarding. Once it knows the destination, it sends data straight to that specific port. Fourth is filtering. It intentionally stops data from going down ports where it just doesn't belong, which saves a ton of bandwidth. And finally, aging.
So why aging? Well, to keep that CAM table from completely overflowing with stale data, switches have an aging timer. On a lot of standard switches, this defaults to exactly 300 seconds. If a computer gets turned off or unplugged and goes quiet for 300 seconds, its MAC address is wiped clean from the switch's memory. This is exactly how the table stays small, lightning fast, and highly accurate.
And that brings us to Section 6, Types of Modern Switches. As we wrap up this explainer, you definitely need to know that if you walk into a corporate data center today, the switches sitting in those racks are not all created equal. There's a massive difference between managed and unmanaged switches. You can grab a cheap unmanaged switch at a big box store, plug your devices in, and it just works. Plug and play. But enterprise network engineers, they rely heavily on managed switches. These let engineers connect directly via a console cable using terminal software like PuTTY. That way they can manually configure security settings, tweak those aging timers, and build out advanced virtual networks.
And as tech has evolved, the lines have gotten pretty blurry. Traditional foundational switches operate strictly at layer 2 of the OSI model, relying purely on MAC addresses. But today, we also have incredibly powerful layer 3 switches. These high-end devices can actually peek up into the network layer and perform routing functions, moving data not just between local computers, but across entirely different IP subnets.
Because there's so much variety, large organizations deploy these devices in a very strict hierarchy to maximize efficiency. Down at the bottom, you have access switches, the workhorses connecting directly to desk computers or printers. Those feed up into distribution switches, which handle the heavier traffic and enforce advanced policies. And finally, those feed up into massive high-speed core switches. They are the beating heart of the network, making sure the data leaving your machine is efficiently distributed across the entire organization or routed out to the wider globe.